Dear colleagues, I am Hikmetcan Çubukçu, medical doctor and specialist in laboratory medicine. In this video, I will talk about risk-based and patient-based quality control and introduce my web-based application, QC Constellation. I have no conflict of interest to declare. In this presentation, I will introduce you the concepts of risk-based and patient-based quality control, covering both theoretical foundations and practical applications. Let's begin with basics of quality control practice. In statistical quality control applications, internal quality control results are commonly evaluated using traditional Hewitt charts, also called as Levy-Jennings charts, in conjunction with Westcott rules such as 1.3s, 2.2s, R4s, and 4.1s. Quality control practices in clinical laboratory environments employ a diverse range of error detection methods, from routine quality control rules to moving averages. While QC rules like 2.2s and 1.3s are effective for identifying significant shifts, trend detection rules such as exponentially weighting moving averages and cumulative sum are essential for detecting smaller shifts and trends. Various applications such as sigmometric measurements and method decision charts are employed to evaluate the performance of analytical procedures. The sigmometric value widely used in industry for decades, and it represents the ratio of process tolerance to process variability. In laboratory medicine, the sigmometric value is calculated using different approaches. Three commonly used formulas are provided on left side. Generally, the bias component is excluded from the calculation. The sigmometric value is interpreted according to the thresholds shown in the table on the right, and a sigmometric value below 2 is unacceptable, while a value between 2 and 3 indicates poor performance. The sigmometric value can also be visualized using method decision charts. In these charts, the y-axis represents allowable bias and x-axis represents allowable imprecision. The measurement procedures imprecision, denoted as coefficient of variation or CVA, is plotted on the x-axis, and if applicable or if present, the bias value is plotted on the y-axis. The sigmometric value of the measurement procedure is then positioned on the chart as a point with a colored diagonal lines representing sigmometric thresholds. In addition to evaluating analytical performance, the sigmometric value is used in risk-based quality control practices to determine internal QC rules and QC frequency. Now we have a fundamental understanding of quality control. Let's proceed to risk-based quality control. The goal of risk-based QC is to select appropriate quality control rule and frequency of quality control measurements to mitigate patient risks. In recent years, concrete advancements in risk-based quality control practices, guided by CLSI documents EP23 and C24, alongside Curtis Parrin's calculations, have emerged. This figure is adapted from Curtis Parrin's article, and here we can see that laboratory testing modes divided in two modes: continuous mode and batch mode. For a batch mode process, a batch, also called as analytical run, includes both patient specimens and QC samples. The key concept from a quality control perspective is that the process is operating in batch units. A batch is either in control or out of control. QC rules applied to the QC samples in each batch determine whether to accept or reject a batch. An intermittent error affects only a single batch. Even if the QC rule failed to detect it, the intermittent out-of-control error condition doesn't carry over to the next batch. On the other hand, a persistent out-of-control error continues to affect subsequent batches until the error condition is detected and corrected. In this example, we can only correct the results of the last batch, because previous batch seems to be in control considering our QC events. For continuous mode process, patient specimens are testing in a continuous stream. Periodically, QC events occur, and a QC event is defined as the point in the testing stream at which QC samples are measured and a QC decision is made. The key quality control concept for a continuous mode process is that the process is operating in sample units, and out of control error condition might occur at any point in the testing stream. Let's look at deeply in the continuous mode. After the in-control QC event at the beginning, an error, so-called out of control condition, occurred, then the subsequent QC event was falsely accepted. Persistent error condition continued, and in the second QC event, we detected a QC rule rejection. In such a scenario, we can correct patient results from the last accepted QC event up to the point of QC rule rejection. These are considered expected number of unreliable correctable patient results, also abbreviated as INUC. However, results prior to the last accepted QC event cannot be corrected, leading to expected number of unreliable final patient results, also abbreviated as INUF. The total expected number of unreliable results includes both INUC and INUF values. What are the risk factors in risk-based QC? Risk-based QC primarily focuses on two main risk factors: analytical performance and the clinical value of the measurement. The risks associated with an erroneous troponin result are not equivalent to those of erroneous lactate dehydrogenase result. Therefore, we utilize the severity of harm category of the measurement as an indirect indicator of its clinical value. Maximum INUF and PFR-based QC plans involve complex probabilistic calculations that consider the error detection probability of QC rules and the expected number of patient samples between QC events. This approach allows us to determine maximum run size, also known as the number of patient results that can be processed between two QC events. Here in the slide, we abbreviated it as MRS. QC Constellation introduces a severity of harm score into the MRS calculation to account for the impact of an erroneous test result. The table on the right summarizes the severity of harm scores and their definitions. While measurements like troponin may be categorized as having catastrophic severity of harm score of 5, measurements such as lactate dehydrogenase can be considered negligible score of 1. To implement a risk-based QC plan, we must conduct simulations of various systematic error levels for selected QC rules and known analytical performance. QC Constellation can perform these simulations instantaneously. Ultimately, we can determine the max INUF value representing the maximum expected number of unreliable final patient results. Additionally, the probability of false rejection can be determined from the power curve of the chosen QC rule scheme. If the probability of false rejection is less than 5%, we should consider using different multi-rule or reducing the frequency of QC measurements. If the max INUF value is less than 6 minus severity of harm score, we must decrease the number of patient samples between QC events or select a multi-rule with more QC measurements. In this slide, we can see the example from QC Constellation, which can easily calculate and simulate such calculations. Max INUF serves as a surrogate metric for patient risk. The probability and severity of harm associated with an erroneous result for that specific test in relation to a patient should also be considered. The recent CLSI EP23 document assists laboratory professionals in assessing their QC strategy in terms of the probability of potential harm resulting from an erroneous test result. Eventually, in this approach, we can calculate reference management index and assess if our QC strategy have managed risks. If reference management index is below 1, the QC strategy is regarded to have managed risks. each approach has some disadvantages. CLSI approach, actually, the document doesn't explicitly illustrate the intricate calculations of probabilities, and also the document doesn't directly assist in determining the maximum run size and proper QC rule. When it comes to MaxInf and PFR-based methods, MaxInf serves as a surrogate metric for patient risks, and the probability of harm to patients due to the inaccurate results reported for a particular test is not based on only the quantity of reported erroneous results, but also on the associated risk factors such as the probability and severity of harm associated with an erroneous result for that specific test in relation to a patient. QC Constellations offer several advantages. It combines the EP23 approach with the MRS-PFR-based approach to provide a more comprehensive and eclectic method. QC Constellation includes the severity of harm category of the measurement in both QC rule and frequency or MRS calculation. Let's continue with tutorial of QC Constellation. Here is our QC Constellation website. QC Constellation is a web-based application, and for your academic use, please cite the reference below. At the left side, we have a sidebar, and this sidebar has these sections for QC management: Levy-Jennings charts, moving average charts, methodicity chart section, risk-based QC parameters section, and patient-based quality control sections. Let's begin with Levy-Jennings control chart. In Levy-Jennings chart section, you can enter your data in this data entry table. And also you can include or exclude your data from using these checkboxes, and you illustrate your data right here. You can also upload your own data. For this, you can click on this Browse Files button and select the data from your computer and upload it. Then there is a drop box that helps you to select the column that to be illustrated on these Levy-Jennings charts. Here is on my example, it is IQC results column. Then I select uploaded data checkbox. Then it illustrates my data instantaneously. I can also click on these checkboxes to illustrate the rules, Westcott rules, to apply these Westcott rules into this Levy-Jennings control chart. We have also a table that shows our analytical performance characteristics, including mean, standard deviation, and coefficient of variation. In my example, my analytical coefficient of variation is 4.81. We can also set our custom mean and standard deviation. Let's set 9 as mean and set 2 as standard deviation and see how the Levy-Jennings control chart changes. Let's go on with moving average charts. Moving average charts section shows a similar user interface, and you can enter your data from this data entry column and also upload your own data from this Browse Files section. When I click on this Browse Files section, I have to select my data to be uploaded, then select the column to be plotted, and afterwards I press on this button, Uploaded Data button, to illustrate my data in these exponentially moving average charts and cumulative sum charts. For exponentially weighting moving average chart, we can select our own weighting factor. You can see that the plot changes with respect to weighting factors. For internal quality control, generally, we have to select a weighting factor from 0.2 to 0.05. And you can track your results from here, and also you can show your plot on full screen mode. Here is our cumulative sum chart, and here is our upper control limit as 5 and lower control limit as -5. It is a conventional control limit that can be seen in Montgomery's textbook, and we have positive cumulative sum values and negative values. And here is our analytical performance characteristics. And also, you can show your data on this table and their corresponding rule-in and rule-out condition with respect to their trend detection rules. And also, you can download your data by pressing this Download CSV file button. Let's go on with method decision chart. In this section, we can calculate our sigmometric value and plot it on method decision charts. We have two main sigmometric formula. One is conventional sigmometric and the other one is alternative sigmometric formula. In conventional sigmometric formula, in numerator side, we have total allowable error minus bias, which is divided by CVA value. And in alternative sigmometric, in numerator side, we have maximum allowable uncertainty or intra-individual or within subject biological variation as numerator and CVA as denominator. Let's show how it works. For conventional sigmometric, I enter some values in here and click on calculate and plot OpSpec chart. And we can show our data right here in precision. CV is 3 and bias is 2%. And my sigmometric value is 3.33, which is between 3 and 4, which stands for marginal performance. We can also calculate our alternative sigmometric value. For that, I enter my within subject biological variation or maximum allowable uncertainty right here. And afterwards, click on calculate and plot button, and it calculates my sigmometric value. We have also normalized method decision chart for comparison of multiple test performances. For that, we enter our test names right here and their respective bias, imprecision, and allowable error values right there. Afterwards, we can see our analytes sigmometric values on these normalized method decision charts. And also, we can show our sigmometric value at the down table. Okay, let's go on with risk-based QC parameters sections. We have two sections for risk-based QC parameters. One is for single rule scheme and the other one is multi-rule scheme. For single rule scheme, we have a 1KS QC rule entry and number of QC. In 1KS rules, we understand from this, for example, if you would like to use 13S rule, you have to enter 3 in this entry box. Or if you would like to 12S, you have to enter 2. But you know that 12S is not appropriate rule to be used. So I keep it as 3 and look at the following steps. So for my measurement, I enter 13% for total allowable error, or maximum acceptable uncertainty can also be entered. And for imprecision, I enter 3%. I have no bias to be entered. So my measurement is potassium. So I would like to enter a critical category. For determining the suite of harm category, you can conduct a survey to clinicians and also laboratory professionals to set suite of harm category for each measurement. For example, for lactate dehydrogenase, you may find out that there's a negligible risk, but for troponin, you may find out that the catastrophic suite of harm category is suitable for troponin. So for potassium, I will keep it as critical. Then I will look at the plots. Here is the plot for relationship between INUF value and systematic error. And here is the max INUF value. And there's a relationship between unreliable results percentage with systematic error and also the number of QC samples with regard to systematic error. And here is risk-based QC parameters table. it says that my probability of force rejection is 0.27%. Sigmometric value is 4.33. And also, we can see here that max inf value 3.41 and also maximum run size as 29. So I enter my maximum run size at the beginning as 50. So let's look at the recommendation. It says that reduce number of patient samples between planned QC to 29 to achieve acceptable max inf. You may also try another multi-rule with higher number of QC measurements. So we can decrease the maximum run size to 29 like that. And it says that it is plausible. And also you can keep it as 50 at the beginning. And you can increase your number of QC measurements. For example, you may use 2 levels of quality control with 1 3S rule. It is suitable for this one. And let's look at the recommendation. Okay, my maximum run size for 1 3S rule with 2 QC measurements is, my maximum run size is 88. So it says that it is plausible. The 50 is plausible. And also I can increase my number of patient samples between planned QCs to 88. Okay. And also my PFR values are within acceptable range because it is below 5%. Let's look at the reference management index, which is firstly introduced in CLSI EP 23 document. And it says that my risk management index is 0.3, and which is within the acceptable range because it is below 1. Here are the probability of harm given an unacceptable result. You can enter this value to find out the reference management index, and also the mean number of days between instrument failures. And also we have to enter the mean number of patients tested per day. Maybe your number of patient samples can be 400. Let's see the result. Okay, it is still acceptable, within acceptable range. And also, maybe your instrument failures are more frequent. Let's enter 45. And you can see that the reference management index is instantaneously calculated. And we have further QC parameters based on specific systematic error of concern. Here are these comprehensive parameters. You can set your own systematic error as standard deviation units and see the results according to entered systematic error. You can see that the changing results. And here is all about the single rule scheme. Let's go on with multi-rule scheme. It has a similar user interface. So here is my multi-rule box. You can select your multi-rule right here. I will keep it as 1 3S and 2 2S rule, and use a similar total allowable error as 13% and similar imprecision value. And my severity of harm category was critical for potassium. And also the number of QC measurements will be 2. And my software is running, and we will see the results within a minute. You can also enter your bias value if available, but generally bias value is omitted in these calculations. So here is the plots that I have outlined. And here is my risk-based QC parameters table. And you can see that my maximum run size is 177 because I changed the rule. I used 1 3S rule, but now I'm using a multi-rule, 1 3S and 2 2S. So my maximum run size increases to 177. So I can run 177 patients between two QC events. And it says that you can increase the number of patient samples to 177. So here I increase my maximum run size right here. We will wait for a while. Okay. Now it is still acceptable, and my PFR value also is acceptable because it is below 5%. Let's look at reference management index. My reference management index is 0.36, so it is below 1, so it is within an acceptable range according to CLSI EP 23 documents. We can also track the further QC parameters based on this multiple scheme. You can click on this calculate based on custom systematic error, and it will open a box to enter your custom systematic error. Let's enter 2 standard deviation of systematic error and see the further QC parameters right here. Okay, so you can see the probe top error detection of this rule, and also percentage of unreliable results and several other parameters, and also the power function plot. So that is all about risk-based QC parameters section. Patient-based quality control offers several advantages over traditional internal quality control methods. These advantages include continuous process monitoring with a commutable and cost-effective approach. This figure outlines the workflow of patient-based quality control. It begins with raw patient data, which must be filtered to select the final data to be used in the patient-based QC analysis. You can apply your own inclusion and exclusion criteria for filtering. For example, you might exclude dialysis patients when performing patient-based QC for potassium. A patient-based QC software should ideally handle both the optimization process to determine optimized patient-based QC parameters, including truncation limits, control limits, block sizes, and transformation type, and also the conventional patient-based QC analysis. It is preferable to first determine optimized patient-based QC parameters, then use them in the real patient-based QC analysis. The patient-based QC workflow continues with truncation of the filtered data and, if necessary, transformation. Finally, the final data is plotted in moving average charts such as exponential weighting moving averages and cumulative sum charts. Let's examine the patient-based QC parameters. Truncation limits are used to reduce population noise and outliers. In this example, we cut the distribution from 2nd and 98th percentiles. Control limits are used to achieve optimal sensitivity and specificity for patient-based QC. In the exponential weighting moving average plot on the right, the red and blue lines represent upper and lower control limits, respectively. During the optimization process, we can adjust these control limits according to sensitivity and specificity values to achieve the best sensitivity and best specificity values. When it comes to block size, a smaller block size can lead to faster error detection, but may increase the risks of false rejection. For example, a smaller block size in exponential weighting moving average corresponds to a higher weighting factor, while a larger block size results in lower weighting factor. In this example, exponential weighting moving average plots illustrates the effects for block sizes of 70 and 10. Here you can see that exponential weighting moving average plot with block size and 10, there are a lot of rejections. There might be some false rejections and real QC rejections. We have also another parameter, transformation. We have 2 kinds of transformation. One is box cost transformation, and the other one is log transformation. These transformation methods used to reduce population noise to adapt our data to our patient-based QC. Optimization procedures involve varying factors such as truncation limits, control limits, and block sizes. And the simulations evaluate different parameter combinations with different degrees of error and identify the set that yields the highest performance. What means the highest performance in patient-based QC perspective? The lowest ANPED and MNPED values, lowest false positive rate, and the highest sensitivity, highest specificity, highest Jordan index. In this example, we can see a simulation conducted by QC Constellation. We simulate different degrees of error rate and see the response of patient-based QC scheme and their ANPDE values, MNPD values, and we found out the best truncation limits, optimal transformation type, and optimal control limits. And we achieved the best performance when we are looking at sensitivity, specificity, false positive rate, NAPD, and MNPD values. So let's go on with our tutorial to see the practical view of patient-based QC. Now we come to patient-based quality control sections. We have two sections. One is patient-based quality control analysis, and the other one is optimizer for patient-based QC. Firstly, we have to optimize our patient-based QC parameters to achieve a proper patient-based QC parameters to be used in our real patient-based QC analysis. So that we have to click on this optimizer for patient-based QC exe button. Then it opens a page and you have to click on this download button and open it afterwards. Here is our desktop application for optimization of patient-based QC analysis. We have two optimization tools. One is for exponential weighting moving average, and the other one is for cumulative sum charts. And actually, at first step, you have to upload your data, which is to be used for optimization process. Here is a template file. I recommend you to look at this template file and prepare your own data according to this template file. So let's upload our data. Okay. Now it opens two drop-down menus. One is for patient results column. I have two columns. One is a result column, and the other one is for days, or you can use batch column for this. So for your example, you should restructure your own data according to this template file. It will guide you for this. So after that, for exponential weighting moving average demonstration, you have to choose your allowable error and also allowable false positive rate. And generally, the allowable false positive rate, the maximum allowable false positive rate can be set as 10%, and allowable error is up to you, your choice. And then you will click on this optimize button and wait for a while to conduct this optimization process. This optimization process includes simulations and optimization of patient-based parameters based on the highest performance can be achieved. So according to the size of your data, it will take 5 minutes to 30 minutes. It depends on the size of your data. So you have to be a bit patient to achieve the optimization results. So let's look at our optimized results, optimized patient-based QC parameters. At the end of this optimization process, we can see our results. In here, it is exponential weighting moving average scheme parameters optimized based on the highest Jordan index. The highest Jordan index actually achieved when our sensitivity and specificity values achieved the highest value. So in this example, our sensitivity and specificity values are 1 as a fraction, 100% for within percentage units. So these are all 100% in percentage units, and also my Jordan index is 1. So it achieved the best performance. And also our average number of patient results until error detection and median number of patient results until error detection should be low as possible during this optimization process. So our software is automatically conducting this optimization process based on the best performance can be achieved. So what are our optimized parameters? We have truncation limits. We can see in here. And also we find out that box cost transformation will be proper for our exponential weighting moving average. And also we have lower control limit, upper control limit, and block size. So we will use these parameters into our actual patient-based QC analysis. Here we have a line plot of ANPED and MNPED versus error rate. Actually, this plot is achieved during these simulations. You can see that we applied positive and negative way some different degrees of errors, and also we recorded the response of this patient-based QC analysis, ANPD and MNPED values. You can see that the ANPD and MNPED values are increases when the error rate is reduced, because when there is no error, the ANPED and MNPED values can be as high as possible. It is a natural thing. It is quite expectable. You can also achieve optimized patient-based QC parameters with possibly the lowest ANPED. Actually, our first results, first optimized parameters were based on the highest Yodan index. I recommend these parameters, but you can also use optimized parameters based on the lowest ANPED value. So the response of your patient-based QC analysis should be will be the fast as possible when you use the lowest ANPED value for your performance goal. So you can see that my sensitivity value is 100% and specificity value is 95%, and my false positive rate is 5%, and Yodan index is 95%. And you can see that these ANPD and MNPD values are lower than the previous optimization process. So you can choose one of them, but we can also have optimized parameters for truncation limits, transformation status, lower and upper control limits, and block sizes for this kind of optimization process. And also, we have our mean and standard deviation of these uploaded data. This can also be used for your further patient-based QC analysis. So we will use the optimized parameters based on the highest Yodan index in the following patient-based QC analysis, and use these optimized parameters in the following section. Until now, we have obtained the optimized patient-based QC parameters, and now we will use these parameters into our real patient-based quality control analysis. So firstly, in this page, patient-based quality control section, we have to upload our own data. For this, you can browse files, click on Browse Files button, or you can just drag and drop your file here. Now I uploaded the data, and it shows a drop-down menu. Select patient results column, then I select my results column, and it automatically illustrates your data, the distribution of your data with histogram. And in our previous section, we obtained our parameters. So I will firstly enter my optimized truncation limits. Let's firstly enter our lower truncation limit as 131, and also the upper truncation limit here. You can see that it cut down the distribution according to these truncation limits. And also, in our previous optimization process, our optimization process revealed that the box cost transformation is needed. So I click on this box cost transformation button, and you see that the distribution is also box cost transformed. You can see them according to the values right here. And afterwards, I come to exponential weighting moving average section. My optimized block size is 10, so I enter 10 in the block size section. And also, I will enter my optimized control limits. So I will enter my lower control limit right here, and also upper control limit. And you will see the updated exponential weighting moving average chart on this screen. Yes, so this is our optimized, ready-to-use exponential weighting moving average chart for our patient-based QC. You can track your data by focusing on this graph and track your data one by one. And also you can show them as in full screen mode. We have also a cumulative sum control chart for patient-based QC. For that, you have to firstly optimize the parameters for cumulative sum control chart using this optimizer tool. Then it will show you that the optimized parameters as truncation limits, transformation status, and also optimized control limit for cumulative sum control chart. And also we can see our data, our all data in this table, and also rule out values in this table. And we can also click on this download button to download our data as CSV file. And that's all for patient-based QC progress.